Which integer n satisfies n to the power of 2006 plus 2n to the power of 2007 equals 3? Well, I'm just going to do this by inspection, and because question number 1, it's most likely very straightforward. So let's try n equals 1. And if you do, you get 1 to the power of 2006 plus 2 times 1 to the power of 2007. And that is 1 plus 2 times 1, which is 3. And there you go. It most definitely matches the right side of the equation. So the answer is n equals 1. If non-equilateral isosceles triangle T, the length of each side is an integer, what is the least possible perimeter? Okay, let's see. So let's try drawing an isosceles. So two sides are the same, and they want the least, so let's start off with the least numbers. So 1, 1, and obviously since it's not equilateral, the third side cannot be the same, so let's make it 2, which is the smallest number other than 1. Now you say, okay, well that sounds pretty good, but here's the problem. It fails the triangle inequality. And what is the triangle inequality? It basically states that if you have any triangle, that two sides, the sum of them has to be greater than the third side. That's the only way a triangle can be made. Otherwise, it would be impossible to make a triangle. In this triangle up here, it fails because 1 plus 1 is equal to 2. It's not greater than 2. So that fails. Okay, no problem. Let's try again. So let's try something bigger. So this time I'm going to make this side 1 because I'm trying to get the least possible perimeter. And then this side I'll make 2 and 2. Now, does this pass the triangle inequality? It most definitely does. And therefore the perimeter is 2 plus 2 plus 1, which is 5. So 5 is the answer to this question, which I believe they are representing with that T. Buses A and bus B always arrive on time. A every 16 minutes, B every 9 minutes. I take 6 minutes to walk to A's stop and 10 minutes to walk to B's. I leave at random times, and I always walk to the same stop. To which stop A or B should I walk to minimize the expected total amount of time I take to walk to that stop and then wait for a bus to arrive? So we are walking toward A or we are walking toward B. And then they are saying that A is every 16 minutes. So 16 minutes, 32 minutes, 48 minutes, 64 minutes, and so on, right? Those are the sort of the arrival times. And then B, every 9 minutes. So 9, 18, 27, 36, and so on. And then the guy, or whoever this person is, he takes 6 minutes to get to A and 10 minutes to get to B. Okay, so let's see here. So the bus takes it arrives every 16 minutes, right? But 16 minutes from the previous arrival. So if it arrived right now, the next time it would arrive is 16 minutes from now. But we have no idea during that time period, like let's say time 0, from time 0 to time 16, we don't know when during that interval he arrives at A. You see what I'm saying? So we have to take the average. So the average is 8 minutes, right? 0 plus 16 divided by 2. I can do it up here. 0 plus 16 divided by 2. 8 minutes is sort of the average. It could be less, it could be more. So he takes 6 minutes to get there, and on average, 8 minutes before the bus arrives. So 6 plus 8 is 14. So 14 is the, I guess, the expected total amount of time that it takes him to walk there and then wait for the bus. Got it? Okay, so the same kind of principle on this guy. 0 to 9 is the range, so the average would be 4.5. So it takes him 10 minutes to walk there, on average 4.5 minutes to wait for the bus, so that's 14.5. So which one is the lower one, because they want you to minimize it? Well, that's this guy, 14. 14 is less than 14.5, so the answer to this question is A. Which of those stops would you go to minimize the expected time? As shown, four cubes with respective volumes 1, 8, 27, and 125 are attached to each other in a way that minimizes the total surface area of the resulting configuration. What is the total surface area of this configuration? All right, so let's do this one at a time. The big one, the one that has a surface area of 125, which is 5 times 5, right? This guy right here. So let's discuss this. So the big one that's at the bottom, let's see here, 1, 2, 3, 5 of those sides are fully visible, or you know, the full surface area is available for calculation. So that's going to be 125 times 5, which is, hold on. Those are the volumes. Sorry, those are the volumes. Sorry about that. The surface area, so let me write that in. Surface area, that's what I'm actually looking at. It's 25. So this would actually be 25 times 5. That's 125. And then the top is interesting. I'll draw it here, or at least I'll try to draw it. So let's see here, we're going to be covering that by this is a 3 by 3, this is a 2 by 2, this is a 1 by 1. So 3 by 3, and this is not drawn to scale, and then this is 2 by 2, and then there's a 1 by 1 in there, right? This is 1 by 1. So 3 by 3 would be 9, 2 by 2 would be 4, and 1 by 1 would be 1. So the top one, we would take the 5 times 5 and then subtract from it that 9, that 4, and that 1. And that's 25 minus 14, which is 11. So we add this and this, and we get 125 plus 11, which is 136. So that takes care of the surface area of the cube, the cube that has a volume of 125. So we can use the same principle to figure out the volumes, or the surface area, sorry, I keep saying volume, surface area of the other guys. So the next surface area calculation is for the 4 by 4 cube. Or is there? No, sorry, there's no 4 by 4. 3 by 3. 3 by 3 cube, making it more difficult for me. All right, so for that one, that's this guy up here, the top one, the biggest one that's sitting on top. Let's see here, 1, 2, 3, 4. There's 4 sides that are full, 4 full sides that are visible. So that's going to be 3 by 3 times 4, which is 36. And then very similarly, I've got to figure out the one that is facing us. The one that's on the bottom, that's completely covered, right? But the one that's facing us, that's covered by a 2 by 2 and a 1 by 1. So that's 4 and that's 1. So that surface area is 3 times 3 minus that 4 minus that 1. So that's 9 minus 5, which is 4. So then we would add that and that. So 36 plus 4, and that gives me 40. So 40 is the surface area associated with the cube that has a volume of 27. All right, so moving right along in the same exact way. Let's move this up a little bit. Now, next one is the 2 by 2. And that one has, let's see here, 1, 2, 3 full sides that are visible in terms of their surface area. So that's going to be 2 by 2 times 3, which is 4 times 3, which is 12. And then the side that is partially covered by just a 1 by 1. So that's going to be, that surface area, this part, is 2 times 2 minus 1, which is 3. So add those two, 12 plus 3, and that gives me 15. So we are almost done. And then the final one is the 1 by 1, and that's pretty straightforward. That's just 3 full sides, I think. And each side is just a 1 by 1. So it'll be 1 by 1 times 3, which is 3. And there we go. So the grand total, let's do it here. Grand total of surface areas would be this 136, this 40, this 15, and this 3. And that all totals 194. So 194 is the answer to that question. The equation 8 times 5 plus 8 plus 5 shows how to represent 53 as the product plus the sum of the same two positive integers. What is the least integer greater than 53 which cannot be represented in this way? Okay, so this is most likely trial and error. Trial and error. So we got to just experiment 54, 55 and see what happens. 56, 57, 58, and hopefully you get an answer. Okay, so let's see. Actually, I'm going to have some sort of a system here, because I'm not going to just sit here and try plugging away, because that's, really a waste of time. Let's see what we can do. If we have a number and it's represented, let's see here, as the product plus the sum of two of the same number. So the product, let's say those numbers are A and B. So that's the first part, plus the sum, A plus B. That's basically what they're saying. Okay. And then somehow I have to manipulate this. So let's see here. If I factor out an A, I'd get B plus 1 plus B. And then if I add 1 to both sides, I think I could factor it a little bit better. Then I would be able to factor out a B plus 1, and that would give me A plus 1. So that's pretty decent, right? That's such a pretty good factorization. So basically what that means is that whatever number we have, if this represents n, all these numbers that are greater than 53, then if you take one more than that, it will be the product of two numbers. That's very helpful. Why? Because if n plus 1 is prime, then it would probably fall apart. Yeah, because these two numbers, A and B, have to be two positive integers. Yeah. So let's see. Which one of these becomes a prime when you add 1? This is 55. That's not a prime. N plus 1 here is 56. That is not a prime. N plus 1 here is 57. I don't think 57 is a prime, right? Because it's divisible by 3. N plus 1 here is 58. Well, that's even. That's definitely divisible by 2. This becomes 59. Aha, 59 is a prime. So let's see what happens. If we have 59, if n plus 1 is 59, and we're trying to make it as b plus 1 times a plus 1, that cannot be done. Now, you might say, well, sure it can. How about if you just have like 1 and 59? There you go, right? But here's the problem. If this is 1 and this is 59, that means b plus 1 is 1. That means b is 0. And that fails. Why? Because they have to be, as we say up here, two positive integers, and b equals 0 is not a positive integer. So that is when it cannot be represented when n is equal to 58. Now, they're saying the least integer greater than 53. I'm sure if you kept going, you could find another one, but they just want the smallest one that's greater than 53. So the answer to this question is 58. If x is equal to 2 to the power of 12 times 3 to the power of 6, and y is equal to 2 to the power of 8 times 3 to the power of 8, what integer z satisfies x to the power of x times y to the power of y is equal to z to the power of z? Okay, so this, I have to do a little bit of manipulation here. The first thing is I'm going to try to do that. So we have x to the power of x and y to the power of y. And this is x and this is y. So let's see what happens. We got, oh boy. Let me just put the x, and then I'm going to keep those x and y's to avoid making this super confusing very quickly. Yeah, just like that. So I think that's sufficient for now. And then let's work with this now. So we have 2 to the power of 12x, 3 to the power of 6x, 2 to the power of 8y, 3 to the power of 8y, like that. And then 2 to the power of 12x plus 8y, 3 3 to the power of 6x plus 8y, like that. Okay, at this point, we will need to do a little bit of substitution here. I could keep going, but I think at this point, so far it's pretty good, but we need to do a little bit of substitution. Okay, now, one thing I noticed is that although they're not identical, the exponents are kind of similar. So let's see what we can do. Let's figure out what is 6x, this guy. What is 8y, this guy, and then 12y. Well, sorry, 12x. Yeah, 12x. Well, 12x would just be this times 2. Okay, 6x would be 6 times x, and x is up here, right? So we have 2 to the power of 12 and 3 to the power of 6. Okay, let me. I need a little bit of extra space here. Okay, so that's 6x. Now, if we were to break that down, it was basically 2 times 3 times 2 to the power of 12, 3 to the power of 6, correct? So that's 2 to the power of 13 and 3 to the power of 7. So that is what 6x is in numbers, because that's what we want. We want numbers. And then 12x is just going to be twice times 6x, so that's 2 times 6x, which is 2 times 2 to the power of 13, 3 to the power of 7. So 2 to the power of 14, 3 to the power of 7. Okay, so that's pretty straightforward. And then 8y, now we have to substitute y, so 8 times 2 to the power of 8 and 3 to the power of 8. 8 is 2 to the power of 3, so then if you combine it, it'll be 2 to the power of 11 times 3 to the power of 8. Okay, so that's exactly what I wanted. Everything is in a number form now. So here we go. Now we got to substitute those guys. 2 to the power of 12x. Okay, so that's 12x. Oh, it's right here. So 2 to the power of 14, 3 to the power of 7, plus 8y. Where's 8y? Oh, here it is. 2 to the power of 11, 3 to the power of 8. And then 3 to the power of 6x, which I believe was this guy up here. 2 to the power of 13 times 3 to the power of 7, plus 8y to the power of 11, 3 to the power of 8. Okay, now we're getting somewhere. Now, I think we have to factor out something. And let's see, what is factorable? I think 2 to the power of 11 times 3 to the power of 7. That can be factored from this and this. And when you do, you get 2 to the power of 3 plus 3. Is that right? I believe so. And then very similarly for this guy, you can also factor out a 2 to the power of 11 and a 3 to the power of 7. And when you do, you get 2 to the power of 2 plus 3, I believe. Yeah. Okay, so now this becomes 2 to the power of 11 times, hold on one second, 2 to the power of 11 times 3 to the power of 7 times 8 plus 11, and then this is 3 to the power of 2 to the power of 11 times 3 to the power of 7 times 4 plus 7, so 4 plus 3, which is 7. Okay. That's pretty decent progress. And then I'm thinking, where do I go from here now? 2 to the power of... okay, since these are the same, okay, I got it. So I can shift this. I can go like this, 2 to the power of 11, 2 to the power of 2 to the power of 11 times 3 to the power of 7. And this same thing, 3 to the power of 7 to the power of 2 to the power of 11, 3 to the power of 7. This is perfectly valid with exponent laws. And then this basically is, you combine it, 2 to the power of 11 times 3 to the power of 7 to the power of 2 to the power of 11 times 3 to the power of 7. And this is, since this and this are identical, it's like z to the power of z, where z would be equal to the 2 to the power of 11 times 3 to the power of 7. So as you can see, it took a little bit of manipulation with the exponent laws, but everything we did was perfectly valid.